again, it's a great honor to give the Coxeter lecture series. I met Professor Coxeter and his wife in Israel in March '82. Perhaps we met a few other times later, but I certainly remember having a hike near the Dead Sea with both of them. I think everybody agreed that he was not only a great mathematician, but a wonderful person. And my lecture will be about challenges in discrete geometry, where I'll try to emphasize on problems. And the first part will be about convex polytopes. Maybe there'll be few things that I will go over to the next lecture, but I hope we can. And I should say, like in a real-life lecture, please feel free to interrupt me, either with chat or just by talking. And if everything is unclear, let me know. And also, I think I try to make the lecture accessible to slightly wider audience than the experts who are in the thematic program. So I hope it will be a relaxing experience for the experts at least. And let me start with the definition. A convex d-dimensional polytope is the convex hull of a finite set of points in Rd, which affinely span Rd. And the polytopes have a face structure. A proper face of P is the intersection of P with the supporting hyperplane, H. And the convex polytope is only finite many faces, which form a partially ordered set. Those are called the proper faces. We usually consider the empty face and the whole polytope as trivial faces. And with the trivial faces, the set of faces is, as I said, a graded, partially ordered set. It's actually a lattice. The intersection of two faces is a face, and the intersection of all faces that contain two faces is a minimal face that contains them both. Fi of P denotes the number of I-dimensional faces of P, and a lot of recent interest was devoted to understand these parameters of polytopes. I should say that the study of polytopes certainly goes back to ancient times. The Platonic solids, which were discovered in ancient Greek, and certainly Coxeter is one of Coxeter's famous books. Regular polytopes was devoted to regular polytopes and more general objects. And it is a fascinating area to study the polytopes under very symmetric polytopes and higher and other combinatorial objects. And this is closely related to Coxeter groups and to Shepard groups. And I will talk I will not emphasize the symmetry, although we will talk a little bit about it later. And we will try to understand the combinatorial structure of polytopes, which is the study of the faces of different dimensions. And perhaps a good point to start is a Euler Theorem, which asserts that the number of, when we have a three-dimensional polytope, the number of vertices minus the number of edges plus the number of faces is always 2. And the Euler-Poincaré formula is an extension to high dimension, and it says that the number of zero-dimensional faces of the polytope, those are called vertices, minus the number of one-dimensional faces, which are called edges. The alternate is sum all the way to the number of d minus one-dimensional faces, which also have a special name, facets. This alternate sum is itself alternating between odd and even dimension. It's equal to 1 minus 1 to the d. So for odd dimension, we get 2, and for even dimension, we get 0. And we can also add the trivial faces to this sum and start with the empty face. And in this case, the alternating sum is always equal to 0. So there is a much interest in the study of phase numbers, and I should mention that one of the holy grail in this field is the so-called G conjecture and G theorem, and various extensions that I will not devote the talk in this direction, although there are some connection, but certainly since my blog was mentioned, you can read there both about the description of the problem and the fascinating recent advances. So I mentioned Euler Theorem, and let me mention also another landmark in the study of polytopes, which is Cauchy Rigidity Theorem. It says that if we have convex polytopes in 3 dimensions, 2 convex polytopes in 3 dimensions with congruent corresponding faces must be congruent to each other. So in dimension 2, there is the famous theorem for triangles, that if you have 2 triangles, that the edge lengths the corresponding edge lengths are the same, then they are congruent. But this is no longer true for polygons with more than 3 edges. And the miracle is that in 3 dimension, Cauchy Rigidity theorem says that this is the general behavior, that once you have 2 polytopes with congruent corresponding faces, they must be congruent. And in the 20th century, I can mention 4 extremely important results in the spirit of Cauchy Rigidity theorem. One was from the beginning of the century by Max Dehn, later followed by Alexandrov, which asserts a variant of the theorem which dealt with infinitesimal rigidity. So I may mention it later, either today or some other time, but it says that the convex polytopes and simplicial polytopes in 3 dimensions are infinitesimally rigid. And then there is a very fascinating and deep high-dimensional extension by Walter Whiteley, and it had a lot of consequences for phase numbers that I'll mention a little later. And on the negative side, there was miraculous examples by Robert Connelly of flexible spheres. So those are embedded spheres. This follows the work by Bricard from the beginning of the 20th century about the flexible octahedra, but Connelly found an embeddings of spheres which are congruent, but which are not which are flexible. They are not rigid, and this implies they are not infinitesimal rigid. And then a later result by Sabitov show that if you have flexible spheres, then the volume is preserved under the flexing, which is also a very remarkable effect. And I should say that regarding Connelly's and Sabitov's theorems, I'm not aware. I think the situation in higher dimension is not clear. Okay, so now I want to start by telling you a remarkable theorem by Bayer and Vilera. And for this, we need to talk about slightly more general parameters, invariance of combinatorial invariance of polytopes than just the phase numbers. And those are called the flag numbers, or sometimes they're called the flag phase numbers. Let's call them the flag numbers. And here, for every time we have a set S of indices, I1, I2 up to Ik, where I1 is greater or equal to -1, greater than I2, and so on, greater than Ik, greater or equal to D, we can count the number of chains of faces, F1 subset F2 all the way to subset of Fk, and here those are faces that deem of the dimension of Fj is equal to Ij. So altogether, we have, okay, so adding -1 and d does not make a difference, but it will still be useful to keep these indices alive. But beside that, we have to start with 2 to the d different parameters. And as we saw already when we count faces, chains of length 1, there is the Euler relation. And it is one of the, I would say, the most exciting problems in the theory, in the combinatorial theory of convex polytope, is to understand the flag number of convex d-dimensional polytopes. And this is a very interesting question. And I think the first step was to understand the linear relation, the linear equalities between the flag numbers. And this is a theorem by Bayer and Bilera that I want, first of all, to describe to you, and then to say a little bit about how it is proved. And they proved that the affine dimension of the space of flag numbers of d-dimensional polytopes is precisely CD -1, where CD is the this Fibonacci number. So C0 is 1, C1 is 1, Ck plus 2 is equal to Ck plus 1 plus C of k, when k is greater or equal to 0. And here you can see this dimension. So when d is 0 and 1, the dimension of flag numbers is 0. For polygons, the dimension of flag numbers is 1. We have one free parameter, which is the number of vertices. Then for polytopes, we have dimension 2, because the flag numbers are determined by the face numbers. And there are three face numbers, but they satisfy one equality, which is the Euler relation. And then in dimension 4, the number is 4, and dimension 5, the number is 7, and so on. And to prove Bayer-Bilera theorem, perhaps let me start with the fact that if we have two faces of, which is of course important in its own right, if we have two faces of a polytope, F and G, where F is a face of G, when it comes to polytopes, the face of a face is always a face, and face of a polytope is always a face of a polytope. And the interval of faces between F and G is itself the lattice of faces of a polytope of dimension, which is the dimension of G minus the dimension of F minus 1. So now we can apply Euler relation for various intervals of this type. And here are some consequences of Euler relation. For example, here is a very simple consequence. F01, so this is the number of chains, vertex inside an edge, is twice F1. This is because every one polytope has 2 vertices. If you think about it, you see that the fact that every one-dimensional polytope has 2 vertices is also a special case of the Euler-Poincaré theorem. And if we sum up over all a one-dimensional face, we get that F01 is equal to 2F1. This is very simple. Here is a slightly more involved identity. So if we have a polytope of dimension greater or equal to 9, F with subscript 1569 is equal to F with subscript 1469 minus F with subscript 1369 plus F with subscript 1269. And how do we see this? We fix a flag of faces. F1 is a subset of F6, subset of F9, where the dimension of F1 is 1, the dimension of F6 is 6, and the dimension of F9 is 9. And now we consider all the faces G between F1 and F6. Those are the faces G between F1 and F6 are in one-to-one correspondence with faces of a 4-dimensional polytope Q. And Euler relation asserts that F0 of Q minus F1 of Q plus F2 of Q minus F3 of Q is equal to 0. And when we sum up over all flags we started with, that F1 subset of F6 subset of F9, then, and here the convention is that the dimension of Fi is I, then this gives us the conclusion that this. So if we extend this idea, I just briefly, I'll briefly tell you what to do. If you have a subset of indices, and now let's consider a subset of indices starting from -1, which corresponds to the empty set, ending with D, which corresponds to all polytope. If we have a subset which contain two consecutive elements, so S contain I and I plus 1, then we consider the maximum element in this flag below S, and let's assume that S always contains a -1, the index -1. This does not make a difference. And then we can express Fs in terms of Fr and Fr union J, where R is obtained from S by deleting I, and then we also allow to add all the indices which are between I and K. So we get here some combination. So if we start with a set of indices which contain two consecutive elements, we get from Euler's theorem by this procedure that I described by the example above, we get this identity that F of R is equal to some alternating. Okay, so F of S is equal to some alternating sum of flag numbers with smaller indices plus either with coefficient 2 or with coefficient 0 F of R. And this gives us an expression of F of S in terms of smaller flag numbers. So the conclusion is that whenever we have a flag numbers with two consecutive elements, we can express it as linear combination of flag numbers with smaller indices, let's say in terms of the sum of the indices. And this means that we can express all the flag numbers by flag numbers of subsets with no two consecutive elements. So those subsets of -1, 0 up to D, which always contain -1 and D, and don't contain two consecutive indices. And the number of such subsets is famously the Fibonacci number. Okay, so this gives us one direction of the Beyer-Billera theorem, and the other direction is harder. For the other direction, you have to construct a Fibonacci number of polytopes so that the flag numbers are affinely independent. And Margaret Beyer and Lou Billera use the following construction. They considered two operations. One is forming a pyramid. So if you have a polytope, you can add a new dimension and a vertex in this extra dimension and take the convex hull. This is a very important construction in polytope theory, in mathematics as a whole. And this is pyramid or cone if you want. And then there is a similar construction where you take a bipyramid, you have the polytope, and you take, again, you add a dimension, you take 1 point above and 1 point below, so that the line interval intersects the interior of the polytope, it takes the convex hull, and this is called the bipyramid. And you can start from a point by applying from the left this word of operation, BP, B, PP, B, PP, BP, and P represent forming a pyramid, B represent forming a bipyramid. And the rule is that you start with a pyramid and you never have two consecutive operation of bipyramid. So this gives you a Fibonacci number of polytopes, and it turns out that the flag numbers of all these polytopes are affine dependent. And I should say that I myself had another construction of such a basis of polytope, which has several other advantages. I can describe you very quickly. Here, you allow slightly more general construction than a bipyramid. You allow to take the join of two polytopes, a join of two polytopes. So if you have a polytope in dimension D and a polytope in dimension E, you can take, you can put them in skew vector space in a space of dimension D plus E plus 1 and take the convex hull. This is called the join. And it is correspond, and the pyramid is an example of a join of a polytope with one point. And then you can do something similar, except you don't take a skew hyperplane, you take orthogonal hyperplane, and you make sure that the origin is the interior point of these two polytopes, and take the convex hull, and this is called the direct sum. And if you repeat the operation of direct sum and joins for certain numbers under certain condition, then you get another class of Fibonacci number of polytopes, which also have affinely independent flag numbers. And this construction has some advantages. For example, it works easily over any field, also over the integers, and it is fairly economical in terms of the number of vertices. So I should say that the first problem, the first challenge I mentioned is to understand flag numbers of convex D polytope. And after you understand the linear relation between linear equalities between flag numbers, you would like to understand linear inequalities and perhaps even non-linear inequalities. And here we mimic what is known for the class of simplicial polytopes, which there is only much fewer parameters, only D over 2, that I didn't get into. And I think we don't expect to have full understanding even of the linear inequalities, but we would like to have better understanding. And I should say that, okay, so I'll mention it later, how we get some interesting inequalities. But let me mention, let me move to other problems. And I should say, one nice thing about mathematics, from time to time, you hear problems not from people working precisely on the combinatorial study of convex polytopes, but from people working in adjacent fields. And Imre Barni is working a lot on random polytopes, and he posed the following problem that we cannot answer. And I should say, at least the first problem, it looks fairly embarrassing that we cannot answer. And here is the problem. Is it true that for every d-dimensional polytope, the number of k-dimensional faces is greater or equal to the minimum of the number of vertices and the number of d-1 dimensional faces, or the number of facets, as they are called? And we don't know even at this. We would expect that when k is smaller than d over 2, then fk of p is greater or equal to f0 of p. When k is larger than d over 2, fk of p is greater or equal to f minus 1 of p. But we don't know this simple inequality, which is a little bit embarrassing. I should say that what we do know is to pose a far-reaching extension of some part of the theory. It's called the upper bound theorem, which will include this special case. So we can embed this simple problem by inside a much more complicated conjecture, where it's not as embarrassing that we don't know how to answer, but we still don't know how to answer. And here is another problem. This is problem number 3. Is there some constant CD so that for every d-dimensional polytope, the number of full flags, so vertices inside edges, inside 2-dimensional faces, inside 3-dimensional faces, all the way to d-1 dimensional faces, is less or equal to a constant, to this constant, times the total number of faces, F0 plus F1, and so on, plus F Again, I don't know the answer. I would guess that, well, I don't want to guess, but I think it would be nicer if the answer is negative, that we don't have such a simple inequality, but I don't know. You can ask it also not for polytopes, for polyhedral spheres, which are more general objects. Okay, let me mention a fourth problem. So here is a nice problem, and here is a little bit of symmetry. This is not this rich symmetry that we see in the regular polytopes, but we look with some symmetry and we consider centrally symmetric polytopes. So a convex body is called centrally symmetric if when x belongs to the body, also minus x belongs to the body. And here's a very simple to state conjecture. Every centrally symmetric d-dimensional polytope satisfies that the number of vertices plus the number of edges and so on, all the way to the number of d-dimensional faces, the polytope itself, is greater or equal to 3 to the d. So the number of non-empty faces is always greater or equal to 3 to the d. And let's see if we have, so the simplex, of course, not centrally symmetric. The simplest in the plane, the simplest centrally symmetric polygon is the square. The square have 4 vertices, 4 edges, and the square itself is 1. So altogether we have 9 non-empty faces. In one higher dimension, we have the cube. So we have 8 vertices, 12 edges, 6 two-dimensional faces, and the cube itself, one 3-dimensional face, the polytope, and this gives us 27. And this is I would say this is a very nice problem. There is a closely related problem that I will mention. The number of faces, you can think about it. The total number of faces you think about is the number of expressing the number of vertices in the barycentric subdivision. You can ask about other face numbers of the barycentric subdivision. And the other question we get, this is called the flag number conjecture. It says that for a centrally symmetric D polytope, F, the number of full chains, F0, 1, 2, up to D minus 1, is greater or equal to 2 to the D times D factorial. And again, we see this number in the cube. The cube has 2 to the D vertices. And when you fix the vertex and you look at chains going from this vertex, the face containing the vertex are in one-to-one correspondence to the face of a D minus 1 dimensional simplex, and the number of such flags is D factorial. So I should mention another, I would say, even more famous conjecture about centrally symmetric bodies. And this conjecture, which is not about phase numbers or combinatorial structure, it is conjecture about volume. And it's called the Mahler conjecture. So Mahler was a well-known mathematician, I think. And he conjectured that for a centrally symmetric d-dimensional body, the volume of K times the volume of the dual polar of K is greater or equal to 4 to the D divided by D factorial. Where do we get this number? If we start from the cube, again, the volume of the cube is 2 to the D. The dual polytope to the cube is the D-dimensional cross polytope. The D-dimensional cross polytope, its volume is 2 to the D divided by D factorial. It can be divided to the D simplices, each of volume 1 over D factorial. So this gives us this formula. And now there is one exciting fact about these 3 conjecture is that the case of equalities, there is a rich a set which satisfy equality, and those are called the Hanner's polytope. So the line segment -1, 1 is a Hanner polytope, and if we have a Hanner polytope, so is its polar P star, and if P and Q are Hanner polytope, so is the Cartesian product P times Q. So P times Q is a Hanner polytope if P and Q are Hanner polytopes, and this implies also that the direct sum of P and Q are Hanner polytopes, because this is the dual operation of Cartesian product. So altogether, when the dimension goes, we have a large number of such polytopes. It's a rich class of polytopes, and it turns out that the equality, every Hanner polytope, every d-dimensional Hanner polytope has precisely 3 to the d non-empty faces. It also satisfies the flag number conjecture as equalities, and remarkably, it's also satisfied the Mahler conjecture as equality. So if you have a Hanner polytope, the volume of the polytope times the volume of the polar is always equal to 4 to the d divided by d factorial. And they satisfy other exciting properties. For example, the so-called Banach-Maser distance. This is a notion of metric defined on centrally symmetric polytopes. And the Banach-Maser distance between the pole and every Hanner polytope is square root of the dimension, which is the largest possible Banach-Maser distance. And it is conjecture that they are the only cases of this equality. Let me mention another problem. So this is more a ad hoc problem. It came up with a discussion by Frege, Hense, Schmidt, and Ziegler about a decade ago. Mainly, it came from computer experimentation. And this conjecture asserts that the number of total flags of a centrally symmetric polytope is greater or equal to d factorial squared divided by 2 to the d times what's called the Mahler volume, the volume of P times the volume of P star. And this is an interesting relation between these two, two of these conjectures. It will imply that if you know the Mahler conjecture, you also can deduce the flag number conjecture. And here there are even more cases of equality, which are quite interesting. So now I want to mention you another bold conjecture, and I will mention a special case a little bit later. I should say that the Hanner polytope also have a nice role for Helly-type theorems, because they are characterized by the property that if you have 2 Hanner polytopes, if you have 3 Hanner polytopes, if you have a Hanner polytope and you take 3 translates so that every pair have non-empty intersections, and all of them have non-empty intersection. This was proved by Hanner himself, and he conjectured that this characterized these polytopes, which turned out to be correct. Okay, so let me mention another conjecture. So I hope you're not too tired of conjectures. Again, if you have questions or remarks, please don't hesitate to share them with us. And this is the cube simplex conjecture. For every k and l, there is a function d of k and l, such that every d polytope, if d is greater than d, k, and l, has either a k-dimensional face, which is a simplex, or an l-dimensional face, which is a cube. When I say a cube, I don't mean literally a cube, but combinatorially equivalent to a cube. So this is it is a very daring conjecture of Ramsey type. I don't know if it's true. And if k and l are equal to 2, let's say you only want that you have a 2-dimensional face, which is either a triangle or a quadrangle. So this is not true in dimension 3. In fact, it's a consequence of Euler's theorem that every three-dimensional polytope has a two-face, which is either a triangle or a quadrangle or a pentagon. But you cannot give up the pentagon because the dodecahedron has all its two faces a pentagon. And I should say that this consequence of Euler's theorem is, there is some debate to the extent whether Descartes already discovered Euler's theorem. And I think there is a stronger case that Descartes already had this consequence that maybe in the dual form, every polytope has a vertex of degree 3, 4, or 5. Okay, now if you move up to dimension 4, the situation does not improve. And this is an opportunity to mention one of the regular polytopes in dimension 4. So in dimension 4, in dimension 3, there are 5 Platonic solids. And in dimension 4, there are 6 regular polytopes. The simplex, the regular simplex, the cube, the cross polytope, and then 3 others. And one of them is called the 120 cell, and it has 120 facets, each of which is a combinatorial equivalent, not combinatorial, each of which is a regular dodecahedron. In particular, all the two faces are pentagons. So, so this conjecture, so what we see here, the D of 2 and 2 is greater than 4. And here is a theorem that says that D22 is equal to 5. And this is the only case of this conjecture which is known. And here is a theorem. Every 5-dimensional polytope has a 2-dimensional face, which is a triangle or a quadrangle. And the way this theorem is proved is as follows. The way this theorem is proved is by proving, it's not so rare, we prove a slightly stronger statement. For every 2-dimensional face, we add a weight, which is the number of vertices of the quotient of the whole polytope with this face, minus 2. So this is a positive integer. And the theorem says that if we sum up this weight over all and multiply it by the number of vertices over all 2-dimensional faces, this is smaller than 5, the sum of these weights over all 2-dimensional faces. And this implies that this inequality immediately implies that for one of the 2-dimensional face, you have a less than 5 vertices. And the way this is proved is that you write up consequences of what you know. You write up inequalities that you know about flag numbers of 5 polytopes, and you add to it the negation of what you want to prove. And I will mention to you what are these inequalities. The first inequality is that in every 5-dimensional polytope, the number of facets is at least 6. So this is a very simple inequality. The second inequality is also a very simple inequality that follows from the fact that a D-dimensional polytope has at least D+1 vertices. But the third inequality is much more sophisticated. It is the sum over all 4-dimensional faces of a certain linear combination of flag numbers, which is non-negative by Walter Whiteley's theorem about infinitesimal rigidity of frameworks based on 4-dimensional polytopes. So Whiteley's theorem, which extends Den's theorem, says that if you have a 4-dimensional polytope and you triangulate each 2-dimensional face by adding diagonals, then this framework is infinitesimally rigid. And from this rigidity, you get an expression for the space of stresses, affine stresses, which is this, which I will not write here, but if you sum up this these quantities over all four-dimensional faces, you get what's written here on the left hand. I think if I put my finger, it doesn't really, you can't see it, but we see this expression. And then when you add these four, when you consider together these four inequalities, you get that they are not feasible. So they contradict each other. The way it was proved was by running a simple linear programming program. But once we saw that there is a contradiction, it was very easy to show the contradiction directly. And the reason this is interesting, one reason it's interesting is that Whiteley's theorem, the consequence of Whiteley's theorem is not known for polyhedral four-dimensional sphere. So this is one of the basic, when we talk about the conjecture, sometimes we try to formulate the most general conjecture, far-reaching conjecture, and sometimes we want to mention the simplest case where we don't know to prove something. And the consequence of Whiteley's theorem, when you try to extend it from polytopes to polyhedral spheres, and the geometric parallel or stronger statement about the generic rigidity of framework based on polyhedral spheres is not known. It is an open problem since the mid-80s, and this is a very interesting problem. And subsequently, this theorem is known for polytopes, but it's not known for polyhedrals. And I should mention a weaker conjecture than the cube simplex conjecture is that there is a finite list of k-dimensional polytope, such that every polytope P, the dimension of sufficiently large dimension, contains a k-dimensional face from this list. So this problem extends already the consequence of Euler's theorem, arguably Descartes' theorem, because we know that this is true for k equal 2. This is true already for polytopes in 3 dimensions. And this is the only case which is known is that every 9-dimensional polytope has a 3-dimensional face with at most something like 200 vertices. So this means there is a list of, I don't know, maybe 2 to the 50 3-dimensional polytopes that every 9-dimensional polytope contain one of them as a 3-dimensional face. And this is also an interesting conjecture. And what is quite curious about this conjecture is that even about the theorem that it uses facts that were initially proved only for rational polytopes. So one interesting fact about convex polytopes is that there are combinatorial types of convex polytopes that cannot be realized when the vertices has rational coordinates. This was first discovered by Micha Perles, who was my thesis advisor, and subsequently examples were found already in dimension 4. And there are some very high-powered techniques that use algebraic geometry that works only for rational polytopes. So for about a decade, this theorem was known for the only case that this theorem was known. It was known only for rational polytopes, but then people managed to extend some ideas from algebraic geometry that use toric varieties and hence use the fact that the polytope is rational to extend it to the non-rational. So I have a few more problems in my that maybe I will not mention right now. I want to mention a theorem, and one reason I want to mention, maybe I will steal a few minutes from the second lecture and mention a few more problems about polytopes and some connection, but I want to mention a theorem because this is a theorem which was proved in the last few weeks by Novik and Zeng, and it says that simplicial d-dimensional polytopes are determined by their graph and the space of affine stresses. So So one of the fundamental results about polytopes is that if you have a polytope, the space of affine dependencies of the vertices determine the combinatorial type of the polytope and even the polytope itself. And this is a very fundamental, and it's called the Gale diagram technique. And there is some sort of high order Gale diagram related to rigidity. And this is conjecture for, so I should say there is also a high version of rigidity that were introduced by several people, but among them by Whiteley and Tay. And it is conjecture that the simplicial polytopes are, okay, it is now known that simplicial polytopes are determined combinatorially by the graph and by the space of affine stresses on this graph. So it's some vector space of weights on the edges of these graphs. And it's also conjecture this works also for higher dimensional stresses. And this is a very exciting development from the last weeks. So I would okay. So let me end by mentioning another very exciting problem about four-dimensional polytope. And this is the problem. Suppose we consider four-dimensional problem, four-dimensional polytopes, and we consider the number of edges. I think Gunther Ziegler had a lot of work, and he introduced this conjecture. We consider the number of edges plus the number of two-dimensional face, and divided by the number of vertices plus the number of three-dimensional faces. And the question is this quantity bounded for four polytopes? And this has some similarity to the second conjecture of Barani that I mentioned. And interestingly, there are examples where this number is unbounded for polyhedral spheres. But those polyhedral spheres are not polytopes. And the world record for polytopes, I think, is smaller than 12. So this is an exciting question about polytopes, which is quite pivotal in our quest to understand phase number